Hi guys, today I'm going to be making a video regarding Demo 4.2, Objects of Different Shape Rolling Down an Inclined Plane. If you're having any trouble with this demo at all, please stay tuned. So Lab 4 is going to be evaluating 3 factors that may or may not affect your rolling speed, and that's going to be your radius, your mass, and your shape. And we're going to see how these 3 components will affect your rolling speed and see how fast the object moves down an incline. Let's start with our first scenario. In our first scenario, we're going to be comparing 3 different shapes, and that's going to be a solid sphere, a solid cylinder, and a hoop that's hollow. And like I mentioned before, this experiment will be dealing with 3 variables, the mass, the radius, and the shape. And so for our first scenario, we're going to keep 2 of the variables the same, and that's going to be our mass and radius. And so the only variable that we're manipulating is the shape. And like I said, we're going to be rolling these objects down an incline at a height of h. Ultimately, we want to see which one of these shapes will roll down the incline the fastest. And so we know that they all start out with some sort of potential energy, and that potential energy is going to be converted into translational kinetic energy and rotational kinetic energy. And so your potential energy is just going to be the simple formula mgh. And that's going to equal the sum of your translational kinetic energy, which is equal to the energy required to linearly move this object down the slope. So this is going to be talking about the rolling speed, and that's going to equal to 1/2 mv squared. And so there's also the rotational kinetic energy, and that's going to be equal to 1/2 I omega squared. The rotational kinetic energy is the energy used to actually rotate the object around its own axis. So what is I? I is called the rotational inertia, but it's also called the moment of inertia. And so I is a measure of the rotational inertia, or how hard it is to change the angular velocity. It's calculated by the sum of the products of the mass of each particle in the object with the square of its distance from the axis of rotation. And so naturally, each of these different shapes have their own moment of inertia. And so for the sphere, it's equal to 2/5 mr squared. For the solid sphere, it's equal to 1/2 mr squared. And for the hollow hoop, it's mr squared. So let's look at our equation again. Our potential energy is going to split up into translational kinetic energy and rotational kinetic energy. And so if we spend more energy on rotating the actual object itself, that means that we're spending less energy on the translational kinetic energy. And since the mgh, the potential energy, is a constant, as one goes up, the other must go down. So we can figure out who will roll down the incline the fastest by looking at the coefficient constants of the moment of inertia of each of the shapes, which is 2/5 for the sphere, 1/2 for the solid cylinder, and 1 for the hollow hoop. The larger the moment of inertia, the slower the object should move down the incline. So ranking these shapes fastest to slowest, the fastest should be the solid sphere, then the solid cylinder, and finally the hollow hoop. Let's move on to our second scenario. In our second scenario, we're going to have 2 different objects, and these objects differ in their masses this time. They have the same radius and the same shape. So I arbitrarily chose 2 shapes of a solid cylinder. I could have chosen 2 spheres or 2 hollow hoops, but I just randomly chose 2 solid cylinders. And so once again, they have equal radius, equal shape, and different masses. And so like last time, our potential energy can be converted into translational kinetic energy and rotational kinetic energy. And this moment of inertia, I, is going to equal, in this case, 1/2 mr squared. And so, like I mentioned before, this is an arbitrary shape. I could have chosen any shape and just compared that as well. And so we're going to treat this 1/2 as a constant A. And so for hoops, that A would be 1, and for spheres, that A would be 2/5. And now let's substitute our moment of inertia equation in, and now we get that the rotational kinetic energy is equal to 1/2 mr squared times omega squared. So looking at the overall equation, we can actually cancel out all the masses. And so because we can do that, we know that mass should not actually affect the rolling speed. And so whether the object is made out of wood, made out of metal, made out of silver, made out of aluminum, doesn't really matter. They're all going to have the same rolling speed at the very end. And so for our final scenario, we're going to be manipulating the variable of the radius. So we're going to keep the masses and the shapes the same. So we're going to be comparing a large sphere versus a small sphere, or a large cylinder versus a small cylinder. So we're going to be manipulating the variable of radius. So just to reiterate, we're going to have equal mass, same shape, but different radii. Writing out our equation again, we're going to have our potential energy being converted into translational kinetic energy and rotational kinetic energy. And the moment of inertia is going to equal to AMR squared, and the A is going to be dependent on the shape once again. So 1/2 would be for like a solid cylinder. And this omega over here is equal to our angular velocity squared. And according to our equation sheet, angular velocity times the radius gives you our linear velocity. So angular velocity squared should equal to our linear velocity squared divided by our radius squared. Let's rewrite our equation and plug in the moment of inertia and plug in the angular velocity squared. And so what do we see? We see that we can actually cancel the r squared in our equation. So what does this mean? Well, this means that the radius should actually not impact the overall rolling speed. And so ideally, objects with equal mass, same shape, but different radii should reach the bottom of the incline at the same time. And as shown from scenario 2, we can also cancel out the masses. So let's rewrite our equation now. So we get that gravity times the height should equal to 1/2 v squared plus 1/2 av squared. And so what does this overall equation show us? Well, this equation tells us basically a synopsis of all three scenarios. It's telling us that mass and radius should not impact the overall rolling speed, but the overall shape does. So let's rewrite our formula again, but this time let's take v squared out. Judging this equation, we know that gravity times height, which is a constant, should equal to v squared times some number. And as this number increases, the v squared must decrease because they're in an inverse relationship and they must equal to some sort of constant. And therefore, for a large rolling speed, we need a small a coefficient. And so what is a again? Remember, we set the moment of inertia to equal to AMR squared, and this A constant depends on what the shape of the object is. The moment of inertia is equal to the summation of the mass times the radius squared. So, in general, a compact mass distribution will allow for a larger rolling speed. So, in general, something that is more compact will reach the bottom of the incline faster than something that is more spread out. So now that you are more comfortable with the moment of inertia, I want you guys to think about this final question. Why is it that ice skaters start spinning much faster when they bring their arms towards the center of their body? Hint, this has something to do with last unit regarding conservation of momentum. If you would like, I encourage you guys to come to the Learning Center and discuss it with a TA or with a professor. I hope this video was helpful, and thanks for watching.